Okay, we're here talking with Michael Skinner, who is a graduate student at the University of Minnesota, chemical engineering and material science, focusing on reaction kinetics. And Michael, why don't you talk about your research poster that you've got up here and what your research is about?
Okay. So the big concept is we have a single reactor tube that's capable of transforming biomass into a biofuel that could be used in today's engines. So this is essentially a two-step process. The biomass will be fed into the top of the tube, which goes over a noble metal catalyst. Some of the biomass is oxygenated to form carbon monoxide, carbon dioxide, and water. And additionally, that provides heat for further reactions downstream. So on the top of the tube, the biomass is broken down into smaller molecules. Then all of that is fed through to a zeolite layer, which acts as a solid acid catalyst, which is capable of removing water. And that's important because in order to form a stable biofuel, oxygen has to be removed from biomass. So one of the ways to do that is through water removal. So the zeolite removes the water from the broken down biomass in the form, removes oxygen in the form of water, and then additionally more zeolite layers would then be capable of forming carbon-carbon bonds as well as branching the remaining carbon molecules to get higher octane or cetane numbers. So as an initial demonstration, we use ethanol as sort of a model compound just to demonstrate that we can take a carbon-carbon bond and a carbon-oxygen bond and remove the oxygen from that molecule. So we have two reactor designs, a parallel ethanol co-feed and a series ethanol side feed design. In the parallel feed, ethanol and hydrogen are fed in the top, and some of the ethanol is converted to C1, so carbon monoxide, carbon dioxide, as well as acetaldehyde. And that's shown in this first bar here, where these are actually the pre-zeolite products here, as well as the pre-zeolite conversion. So after the platinum layer, the remaining ethanol passes through a zeolite layer, where it's dehydrated to form ethylene, the blue, and diethyl ether, the orange, both of which are dehydrated products. So one of the initial problems with this reactor design was the amount of acetaldehyde, that's the red, formed here, because we found that that acts as a protein precursor, which inhibits the dehydration capable in the zeolite. So to get around this, we did a series design where methane is fed up top into the initial platinum layer to provide heat for the reactor, while ethanol is fed through the side. The ethanol then experiences lower temperatures, so it doesn't form acetaldehyde. This ethanol then passes through the zeolite and gets converted again into ethylene diethyl ether. And here you can see we're actually able to get near 100% conversion of ethanol to ethylene, which basically means we could remove all of the oxygen from ethanol, which in the future points us in the direction that we can actually take biomass and indeed remove water from it while keeping carbon-carbon bonds intact.
Essentially turning ethanol into a more traditional petrochemical feed.
Yes.
Okay. And how many years in the future do you see a technology like this becoming viable and out in the mainstream?
There's a lot of fundamental research that needs to be done. This is the first time that a zeolite has been incorporated to a short contact time reactor. Mm-hmm. So, I mean, that's kind of puts us at, the decade range or so before you'd actually see this in a commercial process. Okay. But the initial indicators show that, this has a lot of potential.
And we'll see you as the CEO of that new company, right?
Sure.
All right. Thank you very much, Michael.
Yep.